Yeah, good morning or afternoon, I guess. There are really two messages in this talk, and I'll give them right at the beginning. The first is cemented faults are quite common, much more common than people typically realize. And the second is we have a great field site for studying these kinds of faults where we can look at them in outcrop, with geophysically, and with hydrologic tools. I'd like to acknowledge Jeff Rawling and Laurel Goodwin, who contributed to the work starting out years ago on the Sand Hill Fault in outside of Albuquerque, and which we published in a variety of places. Faults and fluid flow. Well, faults have basically two impacts on fluid flow. The first is as a barrier. The second is a conduit. Barrier for flow normal to the fault. Conduit for flow parallel to the fault, principally in the damage zone around the fault core. There are a variety of mechanisms which lead to these two configurations, or having them both occur simultaneously, such as juxtaposition, fracturing, cataclasis, cementation, brecciation, and the like. We're going to focus mainly on faults as barriers in this talk. Jonathan Kane and others have tried to diagnose the morphology of different kinds of fault styles and how they affect fluid flow, and this is sort of a cartoon of that. We're focused mainly on the kind of localized barrier fault. I got to find a pointer here. That's it right there. So we're looking mainly at the kind of fault that's shown in the lower right-hand side. Fairly thick because of the cemented area, and low permeability with relatively little parallel to fault enhancement, at least in the modern fault, not necessarily in the historical or geologically historical fault. These things, of course, are motivated by a wide variety of applications, from petroleum to groundwater to CO2 sequestration to waste disposal and the like. So we have a lot of reasons for looking at these kinds of things. This is another picture of the Sand Hill Fault. Cemented. Fault zone cements are caused by groundwater flow. The cements end up creating a barrier to flow so that cross-fault flow is limited, and they're usually ignored. Mostly people look at a fault and worry about clay smear or juxtaposition as being the primary cause of the barrier. But cements are much more common than people typically realize and can clearly create a barrier. And the fault we're going to study today, in fact, is sand and gravel. On sand and gravel, there is no clay to smear. Typically, when people go to study faults, they study them at the outcrop scale, maybe at the core scale, and from those try to then project to what may be happening in the subsurface in a petroleum reservoir or an aquifer or the like. When they do that, they use imaging techniques, say from geophysics, to try and figure out what's going on. They may conduct a well test of some kind where they pump or inject and then treat the fault as simply a barrier or as a conduit, but do nothing more sophisticated than that. There's a disconnect across scales. Where we really get our major understanding of faults is at the outcrop or in the little core. Where we apply it is at a much larger spatial scale in the field, in a reservoir or an aquifer. And we have very few sites where both of these things occur together. So if you look at the quote at the bottom, you can see that, well, I can think of less than a handful of sites where you actually have a fault that you can see and a well test you can do located very close to each other. That's not true here for the Loma Blanca study. This is a fault north of Socorro, New Mexico, and south of the Rio Salado. That's that little band in the background there. You're looking north, and there's a shark fin fault cemented zone sticking up in your face. This is a partially cemented normal fault in the Rio Grande Rift. It consists of a bunch of styles of faulting, but the principal one of concern here are the cements, which are what reduce permeability. And it's this unique opportunity of co-located geology observations at outcrop scale, geophysics in the subsurface, and hydrology in the subsurface that makes this particularly valuable. Here's an aerial view, a satellite view, the Rio Salado at the top. The fault comes down this way. The photo we were just looking at was taken down here. And we've done resistivity and other kinds of geophysics across the fault to understand its configuration. It's about 2 to 5 meters thick of calcium cemented carbonate fault. The thickness and the nature of that cement varies along the fault. It seems to have a close association, the cements seem to have a close association with coarse grained materials in the fault for reasons we'll see in a couple of minutes. Okay. So we have a hypothesis or a question that relates to that the degree of cementation and its continuity are key control on the cross-fault permeability and groundwater flow in this situation. We're using geophysical and geological observations, both of the fault architecture and its cements, and related groundwater testing to look at both the permeability and the cross-fault flow. Peter has been doing the geological observations. This is a diagram of a 4-kilometer transect north to south of the fault. The cements are in some places are continuous. In other places, the style is that of concretions. The cements in some cases are really thick, 5 meters, and in other cases substantially less thick. And he's diagrammed where the fault outcrops at the surface, those different styles that are present. And we're doing a wide variety of other characterization methods, including in the future some mini permeameter tests on the fault and parent material surrounding it. There's strong evidence in these observations that fluid flow has controlled the spatial distribution of the cements in the fault. And some of the evidence for that is there's insufficient internal calcium to supply the materials needed for the cements, that the cements tend to occur in high hydraulic conductivity or permeability zones and in very coarse-grained sediments, suggesting that flow controls where the cements occur. There are other potential or related mechanisms for this. One is degassing of carbon dioxide. We sit right above the Socorro magma chamber, and we could have an influence from that. We have a fluid mixing hypothesis where shallower fluids may mix with deeper fluids, leading to mixing-related precipitation. And of course, microbially mediated reactions are a possibility that needs to be considered. And we're investigating these various hypotheses about what causes cements. The geophysics include transects across the fault. Here's the one we've done not too far from the Rio Salado, led by Glenn Spinelli. The upper uninterpreted diagram shows you some shallow sediments, basically a sand sheet sitting over more lithified sandstone bedrock. And you can see the change in depth here of the shallow sediments interpreted below to be a normal fault, dipping at about the right angle for this part of the Rio Grande rift. So it looks like we pretty much have the kind of behavior we would expect to see in this fault. That's about 10 centimeters of sand sheet here, another 15 over here, a fault throw about 15 meters. Flow in the groundwater is from west to east across the fault. So we've also collected GPR data and planned additional transects, 10 or more, with resistivity, GPR, and other geophysical techniques to continue to diagnose what's happening in this fault system. What about the cements? Well, the resistivity will tell us something about the cements, as well as we can interpret it. This resistivity is going to be sensitive to moisture content and mineralogy, both of which will be different in the cements. But our main tool is going to be induced polarization, which defines the ability of the subsurface to store an electric charge, sort of analogous to a capacitor or a battery. And due to differences in chargeability of the minerals in the subsurface that we can detect with induced polarization, we should be able to understand what the spatial distribution and continuity of the cements are going to be in this system. And this is an idea that was first observed by Conrad Schlumberger back at the beginning of the days of resistivity, when he noticed when he turned his resistivity unit off, the signal did not rebound instantaneously to the ultimate one, but rather decayed one way or the other. And observing that decay is what we use to infer this induced polarization in the system, and therefore the chargeability of the material that we're looking at, and then the presence of cements. So we've been doing resistivity surveys. We're planning to do some induced polarization. We're going to do hydrologic testing across the fault. Along these transects, We're going to take a couple of them, one with more degree of cementation and one with less, and do pump tests on each side of the fault. We have an existing pump test right up here to the upper left with multiple observation wells nested over the depths. Here's the pumping well. So we have a lot of characterization information. Here's some semi-log plots of drawdown and some piezometers located at the same point at different depths to illustrate the kind of information that's available now. But what we want to do is go out and do the same kind of thing, but immediately adjacent to the fault, looking at aquifer properties, fault properties, orientation, thickness, and continuity, fault normal, permeability, and groundwater flow, testing both cemented and uncemented zones, and a variety of tests. We're going to look at single well pump test on one side of the fault, then do another pump test on the other side, and we're going to look at pumping and injecting across the fault, all of which will tell us something about what's going on. So here's a sort of idea of what this might look like. Here's a fault with a pumping well nearby. We've had recent solutions for pervious seals. It's not just stuff you can do in a first-year course in groundwater hydrology. This is a semi-log plot of drawdown in the pumping well taken from the petroleum literature, showing that eventually after wellbore storage effects and the like, you get a straight line radial flow response to the system. If there's a fault nearby, you get another straight line segment with a different slope. The location where the break in the slope occurs tells you where the fault is. This is homework stuff, all well known. But what's not well known in the hydrology literature is you can do the same thing for pervious faults and get a whole array of different responses in between those two end members. And you can do this not just for the pumping well, but for observation wells. And of course, observation wells are key to doing this. We haven't done this yet. It's a work about to be taking place. And we know that we're going to need observation wells on both sides of the fault. Here's a diagram of the kind of drawdown you might expect to see. At the top is a single well test. The fault is sort of in the middle, the well slightly to the right. At the bottom is a doublet well test where we're injecting on the left side and producing on the right side. As you go across this diagram, the leftmost pictures depict what happens if there's no barrier present. It's just basically infinite aquifer kind of flow. The right one is we have a perfect seal. Those two end members are homework problems. The one in the middle is the one with a pervious fault. And if you look at these patterns, you can see that with observation wells supplemented by geophysical detection of drawdown, we can infer what the impact of the fault is, including more sophisticated inversions than you might do with this, accounting for heterogeneity of the fault and of the aquifer material, and in 3 dimensions. So our basic idea here is that we're going to have a novel, this is going to result in a novel fault zone permeability model based on the integration of geophysical, geological, and hydrologic data, and that this site provides an opportunity to develop an integrated data set that includes previously unavailable 3D data on the spatial distribution of fault and materials and properties, as well as characterization of the hydrologic impact of that. And what we'd like to do is invite anybody here who'd like to join us in this unique site, bringing together geology, geophysics, and hydrology to do characterization and modeling and investigation. We would encourage you to talk to myself or Glenn Spinelli, who's in the back of the room. Thank you very much.
All right, we have time for a quick question for John. Anybody have a question?